Let's look at a problem for tension design using LRFD that involves us figuring out what tensile load a member can support and whether the member is adequate for a load that's described. In this problem, we're going to consider two different types of failure. We're going to consider yielding, and we are also going to consider rupture. For this problem, we're not going to consider block shear, as that's its entire own problem and requires a separate video. But for this problem, what are we given? We have an L 3x3 by ½ inch angle, meaning we have two legs that are 3 inches long each and the thickness of a ½ inch. We're told that we are using A36 steel and that we are using a connection designed out of 3/4 inch bolts. We're not given any information about the gusset plate, so we're going to assume that our failure is governed by the angle, and we're going to use that to figure out where our yielding and rupture limits are. So considering that we're using the LRFD design system, we have two different equations. We're going to have one for yielding, and we're going to have one for rupture. And this one right here is going to be your yielding equation. This one here is going to be your rupture equation. To go through these terms real quick, we have PU, which is the sum of the factored loads, has to be less than or equal to our resistance factor times our yield strength times our gross area, and this governs yielding. The resistance factor in LRFD for a yielding situation is 0.9. For rupture, we have Phi-T, that resistance factor, which is 0.75 times the ultimate stress times our effective area. And effective area is an interesting concept. So effective area is our net area, which would be our gross area, so what we used up here, minus the area taken up by the bolts, times U. And U is our shear lag factor. Shear lag is an interesting phenomenon, but we luckily are given a table for it in the AISC manual in table D3.1. This is a very useful table for any sort of connection design where we have bolts or welds, which is, it's pretty much all connections. And we are looking at a case 2 situation here. So if you want to look through the table, you can get a better understanding of what these different cases are. But for the purpose of this, we're going to remember that U is going to be equal to 1 minus X bar over L. What I already had here, I just wanted to write it again. X bar is going to be given to you from table 1-7 here, because we are looking at an angle. L is going to be the length of the bolt connection. Yep. So if we look up here to our diagram, the length of the bolt connection is from here to here. So what we have is L is 6 inches. Okay. So how do we go through and do this problem? Well, we'll simplify some of our equations real quick, or not simplify, I should say, but we'll rewrite some of our equations real quick so that we remember what's actually happening. So since we're talking about LRFD, we mentioned that we have our sum of factored loads has to be less than or equal to our our resistance factor times our nominal strength, and that is our design strength, right? So we need to find this twice because we have two different failure states. So let's start with yielding. For this, it has to be less than or equal to Phi-T. We can break this out, Fy Ag. We can keep writing this down. We're going to have 0.9 is our yielding resistance factor times a 36 KSI yield strength, because it's A36. And then our gross area, we're going to go to table 1-7, and we're going to find that our gross area is 2.76 inches squared. I am not always the best about this, but I highly recommend you do all of your problems recording your units meticulously. It's going to save you a lot of time, especially when you get into problems with beam design and these different variables that you come up with. It makes it a lot easier. So PU is going to be less than or equal to 89.424, and this is in kips, because we have KSI times inches squared, and Phi-T is unitless. So for yielding, we now have our strength. Let's go and do rupture. We're going to start with the same basis, because we're still talking about the same type of failure. It's still a tensile failure, but now we're looking at rupture. And if we break this down, we have phi t times Fu, which is our ultimate strength, times our effective area. We can break this down further. Phi t times Fu times An times U. So let's go through these one by one. Phi t, I shouldn't write that again, is 0.75 because we're talking about rupture. We have 58 KSI because we're talking about a rupture situation here, and the ultimate strength of A36 steel is 58 KSI. But then we have AN. How do we get AN? So AN is going to be equal to the gross area minus the sum of the diameters of the bolts times the thicknesses of the bolts. And don't forget to multiply by the thickness, because I do that all the time. So we were given that it's 2.76, and then we need to look back at our diagram and see what our cross section is going to look like. So if I were to draw this out from the side now, I'll draw my little angle here. Excuse the draw. Oh boy, that is not what we're looking for. We can say it's going to look something like this, and we're going to have this hole in the middle here, right? So we need to subtract that area that is taken up by the bolt hole from the gross area, and that'll give us our net area. So if we come down here, that's going to be the diameter of the hole, not the bolt. So we're looking at 3/4 of an inch plus 1/16 for roughness as specified by AISC, pardon me, plus another 1/16 for spacing so that the bolt is able to fit in. If you have a 3/4 inch bolt and you try to fit it in a 3/4 inch hole, it's not going to fit. Then we need to multiply by the thickness of the angle, and we only have one hole, so that's going to be it for this. So 2.76 minus, that is 7/8 times 1/2 is going to be 2.32 inches. And I'm just going out to two significant figures for this problem. If you're using your calculator, you can follow along with as many significant figures as you'd like, or it produces. So this is 2.32 inches squared. I'm going to move that text up a little bit because that's starting to get in my way here, and I don't want that to happen. Okay, now we have this, but we still need U, right? So I mentioned that we're talking about case 2, and this is actually what's going to give you the most accurate shear lag factor for this. But there's another more general case you can use. I don't have the table open in front of me right now, but there's sometimes you can generalize and say that for a connection like this, U might be equal to be 0.6 or 0.8, depending on the number of holes and fasteners when you're looking at an angle. But we're going to do the more precise method for right now. We're going to have 1 minus X bar, which is given from the, remember this is from table 1.7. That is 1.6, or pardon me, no it is not. It is 0.929 for a 3x3.5 inch angle. And then L is the length of that connection. So we had mentioned that was 6 inches earlier. So we'll just plug this in real quick, and we get our shear lag factor is equal to 0.845 for a connection, for this connection. So we can now just plug this back in up here. And now we have what we need to determine what the design strength is. So that number is going to come out to be 0.32 times 58 times 0.75, 85.29. 29 kips. So if we compare this to, I should have gone out to 3 decimals for this. 2.94 is what I'm getting, but I might have a rounding error there if you have something different. Now, if we look at this problem, we see we have established our 2 yielding states that we're our 2 failure states that we're looking at. Which one is going to govern though? Well, rupture has a lower value, so rupture is going to govern at 85.294 kips. But the problem asked us to do something else, so we're going to run through that real quick. The problem also asked us, is the member adequate for the load that's applied? I have a 25 kip load drawn up here, so we're going to assume that this is a 25 kip live load, and we're going to go through and figure out real quick whether that changes our equation or whether the member is actually good. So 85.294 would be the most that PU would be allowed to be, right? Because PU has to be less than PU, which is our sum of the factored loads, has to be less than or equal to our design strength. So we're going to find PU right now. Without going through all 5 of the LRFD equations that we can use, I can tell you right now that equation number 2 is going to govern, and we'll have 1.2 dead plus 1.6 live. But since we only have a live load, PU is going to be equal to 1.6 times 25. You can probably guess already that that's going to be 40. And with 40 kips, we have PU. So 40 has to be less than or equal to 85.294, which it is. So, since that is the case, the member is adequate. And that is the end of this problem. I hope you guys found this really helpful, and stay tuned for more cases in the future. See ya.